We have discussed angles measured in degrees, but now we want to discuss angles measured in radians. First, let's talk about what 1 radian looks like. If I have an angle in standard position with its vertex at the center of a circle, our angle theta here would be called 1 radian. We define 1 radian by how much of the arc the angle intercepts. If our angle intercepts an arc length equal to the radius, so here's the radius of our circle, if the intercepted arc equals to the radius, then we call that 1 radian. When we define radians, we are going to define it in terms of the arc length. We will describe our angle theta as the arc length divided by the radius. If the arc length that is intercepted by our angle, if that arc length is equal to the radius, then we get 1 radian. So theta is equal to the arc length, which for this example is r, divided by the radius. And if the arc length is equal to the radius, then r divided by r would give us 1. So we would say that that is 1 radian. So now we define radians as the arc length divided by the radius. 2 radians, an angle measured as 2 radians, would have our angle in standard position, and the arc length, for the arc length I will be able to lay 2 radii or 2 radiuses on the edge of our circle. So 1 radius, 2 radius. Since the arc length measures 2 radians, that would be 2r divided by r. Then theta is equal to what we call 2 radians. So it's the arc length divided by the radius. Here we have something that is half a radian. So here is my angle theta in standard position, and the radius is here. And if I was to lay the radius on the edge of my circle, we see that that would be too big, that the arc length intercepted by the angle is only this long here. And that is what we would say half a radius. So half a radius is my arc length divided by the radius. The r's would cancel, and we would say that we have an angle measured as half a radian. So if our angle theta, if we have a complete rotation, if our angle theta is measured in radians, then we would have to define it as the arc length of a complete rotation, so the arc length of the entire circle divided by the radius. Well, the arc length of the entire circle is called the circumference of the circle, and the formula for the circumference of the circle is 2 times pi times r. And if I divide that by the radius, the r's cancel out and I end up with 2 pi. So a complete rotation all the way around a circle would be 2 pi radians. Now this would be the exact value. If I wanted to find an approximate value for that, we know that pi is approximately 3.14. So 2 times 3.14, our approximate value would be 6.28 radians, and that represents a complete rotation all the way around our circle. Now what that means is that a complete rotation, if I look at the circle, I should be able to fit 6 radius on the edge of the circle. So 6 radiuses, or 6 radii. So 1 radius is here, so that would be 1 radian. I can fit in another radius, that would be 2 radians. Another radius, that would be 3 radians. We can see that we haven't done quite a complete half rotation here. We're almost to the half rotation, but not quite. We have to go a little bit more. So let's keep going. And we could fit another radius on there, so this would be called 4 radians. Here, this would measure 5 radians. And then another radius that would measure 6 radians. So we see that we need 6 radians laying end to end on the edge of my circle for a complete rotation, and then a little bit more. So all the way around would be 6.28 radians. In the past we have talked about degrees, 360 degrees used to represent a complete rotation in degrees, but now that we're measuring in terms of radians, 360 degrees is equivalent to 2 pi radians. So these really represent exactly the same thing, a complete rotation all the way around a circle. This is just two different ways of measuring that complete rotation, in terms of degrees and in terms of radians. Now, if I divide both of these sides by 2, I get 180 degrees is equivalent to pi radians. So half a rotation is actually equivalent to pi radians. And that makes sense because a half rotation was a little bit more than 3 radiuses, or a little bit more than 3 radians, and pi represents 3.14. So that makes a lot of sense. Now, if I wanted to divide that in half again, we would see that 90 degrees is equal to pi divided by 2. So where we used to have 90 degrees, now we will have pi over 2. And if you put pi divided by 2 in your calculator, you get approximately 1.57 radians. And that makes sense because we had 2 radiuses laid end to end, and 90 degrees came in between 1 and 2. So it looks about halfway between 1 and 2. So this is pi over 2, pi over 2. Every 90 degrees represents pi over 2. So 2 pi over 2, so if I have 2 of those, that would be pi. And then 3 pi over 2 would be what we now call, what used to be 270 degrees. And that now, as an approximation, is a little bit more than 4. It's in between 4 and 5. Looks like it's closer to the 5. So that's 4.71 radians if you put that into your calculator. And then as I go all the way around, of course, we get back to 2 pi. Here we have an animation that shows a circle with radius r. If we take that radius, the length of the radius, and lay it on the edge of the circle, marking off 1 radius on the edge of the circle, then that angle would be measured as 1 radian. 2 radiuses on the edge of the circle would measure 2 radians. 3 radiuses on the edge of the circle would be 3 radians, and a little bit more gives us 3.14 radians or pi radians. That represents half the circle. If pi radians represents half the circle, then 2 pi radians would represent the entire circle.